right? Probably the most famous scientist alive.
Mm-hmm.
And he's working on two massive, um, groundbreaking ideas at the same time, ideas that would completely change how we see the universe.
Yeah, completely different directions, seemingly.
Exactly. On one side, he's really bothered by quantum mechanics, all that weird probability stuff. He comes up with this challenge, the EPR paradox.
Right. Questioning if it was even a complete picture of reality.
And then totally separately, he's digging into his own theory, general relativity, exploring space-time geometry, figuring out these cosmic tunnels.
The Einstein-Rosen bridges, wormholes as we call them now.
Right, wormholes. So for almost 80 years, these two huge ideas from the same guy lived in separate universes, intellectually speaking.
Completely disconnected.
But what if they were connected all along? Two sides of the same coin.
Well, that's the really exciting idea behind the EPR conjecture.
Yeah.
Juan Maldacena and Leonard Susskind proposed this back in 2013.
ER EPR.
Yeah, it's a pretty stunning unification, bridging almost 100 years of physics.
Okay.
So our mission today in this deep dive is to walk you through this.
Okay.
How Einstein's famous Stucky action at a distance, quantum entanglement, might actually be the same thing as a geometric wormhole.
Wow. Okay.
And what that really means for, well, space-time itself. So you're basically getting a shortcut here to understanding one of the biggest mysteries, one of the most cutting-edge ideas in physics today.
Fantastic. So let's go back. 1935, the EPR paradox. Why was Einstein so, unhappy with quantum mechanics? What led him, Podolsky, and Rosen to write that paper?
Einstein just wasn't comfortable with it. He felt reality should be definite and local. Things have properties whether you look or not, and nothing travels faster than light.
Makes sense. Classical intuition.
Exactly. So their 1935 paper basically asked, is the quantum description of reality complete? And it was built on two sort of core ideas he thought any complete theory must have.
Okay, what were they?
First, his criterion of reality. Basically, if you can figure out a property of something with certainty without messing with it, then that property must be objectively real.
Right. It exists independently.
Mm-hmm. And second, locality. No spooky action at a distance. Cause and effect can't happen instantly across space.
Got it. And this leads to that famous thought experiment with the entangled particles.
That's the one. Imagine you create two particles, A and B. They're entangled, their fates are linked, perfectly correlated, even if they fly light years apart.
Okay.
Now, Alice has particle A. She decides to measure its position. Because they're entangled, she instantly knows B's position too, perfectly, without ever touching B.
So by Einstein's rule, B's position must be real.
Exactly. But here's the kicker. Alice could have chosen to measure A's momentum instead. And again, entanglement means she'd instantly know B's momentum with certainty. So B's momentum must also be real, according to Einstein.
Wait. Definite position, A and D, definite momentum at the same time. That's impossible, right? Heisenberg's uncertainty principle.
Precisely. That's the direct contradiction. Heisenberg says you can't know both perfectly. So Einstein's conclusion was, quantum mechanics must be incomplete. It's missing something if it can't describe these supposedly simultaneous real properties.
Okay, so that's a huge challenge to the foundations of quantum theory. How did people like Niels Bohr react?
Bohr fired back pretty quickly. He didn't argue with the math, but he fundamentally disagreed with Einstein's starting point, especially that criterion of reality.
How so?
Bohr argued that you can't talk about a property separate from how you measure it. The experimental setup defines the property. Measuring position and measuring momentum are like mutually exclusive contexts.
So you can't mix and match realities from different experiments.
Right. For Bohr, there was no paradox because the idea of particle B having both definite position and momentum simultaneously was flawed from the start. You simply can't set up an experiment to see both at once.
So it became a kind of philosophical debate.
For decades, yes, until John Stuart Bell came along in 1964. He devised these mathematical tests, Bell's inequalities, that could actually distinguish experimentally between Einstein's local realism and quantum mechanics.
And what did the experiments show?
Starting with the Lane aspect in the 1980s, the experiments came down decisively against Einstein. They showed Bell's inequalities are violated, just like quantum mechanics predicts.
Wow. So the spooky action is real, experimentally verified.
Absolutely. It's not just a weird theoretical quirk. Entanglement is a fundamental feature of our universe. Particles really can share a single quantum state instantly correlated no matter how far apart. It's mind-bending, but it's real.
Okay, so while Einstein is wrestling with quantum weirdness, that same year, 1935, he's also doing something completely different with general relativity. The Einstein-Rosen bridge, what was going on there?
Yeah, totally separate track. This paper was with Nathan Rosen, and their goal wasn't, finding shortcuts across the galaxy. It was more theoretical.
What were they trying to solve?
They were trying to get rid of singularities, these points of infinite density, like at the center of a black hole, which pop up in classical physics. They wanted to see if particles could be represented as, like, smooth features of space-time geometry instead.
Okay, how did they do that?
They started with the known solution for black holes, the Schwarzschild solution from 1916, which has that singularity. Einstein and Rosen found a mathematical trick, a change of coordinates that seemed to smooth it out.
That created the bridge.
Effectively, yeah. Their math connected two separate regions of spacetime with a kind of tube or throat. That's the Einstein-Rosen bridge. It's funny, Ludwig Flamm actually found something similar way back in 1916 too, but it didn't really catch on until Einstein and Rosen.
And John Wheeler gave it the catchy name Wormhole later on.
That's right, in 1957. Much better name.
So you have these two incredible ideas from Einstein in one year. Spooky entanglement and space-time wormholes, seemingly unrelated.
Yeah.
But could you actually travel through these wormholes?
Well, there's the catch. At least for the ones Einstein and Rosen described, the answer turned out to be a definite no.
Why not?
John Wheeler and Robert Fuller showed in 1962 that these specific types of wormholes are incredibly unstable. The throat opens up, sure, but then it collapses back down to a singularity so fast.
Too fast for anything to get through.
Exactly. Not even light could make the trip. They're non-traversable. To make a traversable wormhole, theory says you'd need this really weird stuff called exotic matter, which has negative energy density. Basically, anti-gravity.
And we haven't found any of that.
Nope. Still purely theoretical. So these 1935 concepts, entanglement and wormholes, remain fascinating but separate for a long time.
It sounds like general relativity and quantum mechanics were kind of doing their own things for decades, until black holes forced them into the same room, so to speak.
That's a great way to put it. Black holes became the ultimate testing ground where both theories had to apply, and that's where the cracks started showing. The first really big one was the black hole information paradox.
Stephen Hawking, right? Mid-70s.
Exactly. Hawking realized that quantum effects near the event horizon, the edge of the black hole, would cause it to radiate particles. Tiny quantum fluctuations create pairs of particles. One falls in, the other escapes.
That's Hawking radiation. It means black holes aren't truly black and they evaporate.
Precisely. They have a temperature, they radiate, and over absolutely immense timescales, they shrink and disappear.
Okay, so where's the paradox?
The paradox is about information. Quantum mechanics has this fundamental rule called unitarity, which basically says information can never be truly destroyed. It might get scrambled, like shuffling cards, but the information is still there.
Right. You can always reshuffle them back.
Theoretically, yes. But Hawking radiation seemed purely thermal, random heat. It didn't seem to carry any information about what fell into the black hole to begin with.
So if the black hole evaporates completely, where did the information go? About the star that collapsed or anything else that fell in?
Exactly. It seemed like it was just gone, destroyed. That's a massive violation of quantum mechanics. It was like burning an encyclopedia and the ashes having zero trace of the words. Don Page later refined this, showing the expected pattern of information release, the Page curve, if unitarity holds, which Hawking's calculation didn't match.
That made the problem even starker.
Okay, that's a serious conflict. But then things got even worse with the firewall paradox in 2012.
Yeah.
AMPS.
Yeah. Ilhari, Muralf, Polchinski, and Sully, AMPS. They sharpened the information paradox into an even more acute dilemma. They showed that some earlier ideas trying to solve it, like black hole complementarity, didn't quite work.
What was their argument based on?
They started with three basic assumptions most physicists accepted. 1, unitarity information isn't lost. 2, Einstein's equivalence principle falling into a black hole should be uneventful at the horizon. No drama. 3, effective field theory, standard quantum mechanics works near the horizon.
Seems reasonable enough. Where's the contradiction? It comes down to something called monogamy of entanglement. It's a quantum rule. One particle can't be maximally entangled with two separate things at the same time. Entanglement is exclusive, like marriage in the quantum world.
Okay. Monogamy. How does that apply here?
Okay, think about a Hawking particle escaping. Call it B. For information to be conserved, unitarity, B needs to be entangled with all the radiation that escaped earlier. Let's call that system A.
Right, so the information gets out.
But for the horizon to be smooth, no drama. Equivalence principle. Particle B also needs to be maximally entangled with its partner particle C that just fell inside the horizon.
Ah, so B is entangled with the early radiation A and its partner C inside.
Exactly. It's maximally entangled with two independent systems, A and C. That's quantum polygamy. It violates the monogamy rule.
So something has to give. One of those three assumptions must be wrong.
That was the AMPS conclusion. And their sort of conservative choice was to ditch the equivalence principle at the horizon.
No more no drama.
Right. Instead of a smooth passage, they proposed a firewall, a region of incredibly high energy right at the horizon that would instantly incinerate anything falling in.
Whoa. So the event horizon isn't this smooth boundary, it's a wall of fire. That's
Very dramatic. It was a huge crisis. Is the elegant geometry of relativity wrong at the horizon? Or is information lost? Or does quantum mechanics break down? It demanded a truly radical new idea.
And that radical idea is ER EPR, the proposed solution. So the statement ER sounds simple, but unpack that for us.
It's incredibly profound in its simplicity. It says, take any two quantum systems that are maximally entangled. That's the EPR part.
Like our particles A and B from earlier?
Yes. Or perhaps two entangled black holes. The point is that these two entangled systems are geometrically connected by an Einstein-Rosen bridge. That's the ER part. A wormhole.
The spooky connection is a physical tunnel through space-time.
That's the core idea. The entanglement is the wormhole. Einstein's spooky action is given a geometric structure. It's not just correlation, it's connection.
Where did this connection come from? It seems like a huge leap.
It builds heavily on something called the holographic principle, and more concretely, the ADS-CFT correspondence.
Okay, ADS-CFT, we hear that a lot. Quick refresher.
Sure. Holography is the idea that all the information in a volume of space can be described by a theory on its boundary, like a 2D surface describing a 3D space.
Like a hologram.
Exactly.
Yeah.
ADS-CFT, figured out by Maldacena in '97, is a specific mathematical example. It says a theory of quantum gravity in a particular curved space-time called anti-de Sitter space, ADS. The bulk is exactly equivalent to a standard quantum field theory, CFT, living on its boundary.
A dictionary between gravity and quantum field theory.
It's a very powerful one. And a key step was the Ryu-Takayanagi formula in 2006. It showed that the amount of entanglement between regions on the boundary CFT corresponds directly to the area of a certain surface in the ADS bulk geometry.
So entanglement literally builds geometry in that picture.
It really suggested that, and ER EPR took that further. They noticed that a specific state in the CFTs, the thermofield double state, two entangled CFTs, perfectly matched the geometry of an eternal ADS black hole, which has two exterior regions connected by an ER bridge. The entanglement was the bridge in this precise case.
Okay, I think I'm getting it. The geometry emerges from the entanglement pattern. So how does this solve the firewall paradox? How does it let us keep both no drama and information conservation?
It elegantly sidesteps the monogamy problem. Remember, particle B escaping the black hole, it's entangled with its partner C inside.
Right.
And it also needs to be entangled with the early radiation A outside.
No quantum polygamy.
But ER EPR says, wait a minute, the interior region containing C is already connected via or wormhole, an ER bridge, to the system of early radiation A. They aren't truly separate systems from the perspective of entanglement geometry.
Ah, so A and C are already linked through this wormhole network.
Okay. Exactly. So B isn't entangled with two independent things. It's entangled with C, which is part of the unified system interior plus early radiation linked by ER bridges. There's only B and the combined A plus C system. No violation of monogamy.
So the firewall just isn't needed. The horizon can be smooth. Information can get out through the wormhole connections eventually, and quantum monogamy holds, because entanglement is geometry.
That's the beauty of it. It suggests space-time itself is woven from these entanglement threads. The no-drama horizon is saved.
That's incredibly elegant, but it's still a conjecture, right? What's the evidence, or are there consistency checks?
It's definitely still a conjecture, but there are strong consistency checks. For instance, people showed that the area of these classical ER bridges obeys mathematical rules like strong subactivity, which entanglement entropy also has to obey. That's a non-trivial alignment.
Math matches up.
It does. But there's a subtlety. These classical smooth wormholes seem to correspond only to monogamously entangled states.
What about non-monogamous entanglement, like three particles entangled together, GHE states?
Right. That's a key point. It suggests ER is a very specific kind of EPR. Smooth space-time geometry seems to require these monogamous entanglement patterns, What geometry corresponds to more complex, non-monogamous entanglement is, well, less clear. Probably not a smooth classical wormhole.
Does that connect to how we'd observe things?
It seems to. Susskind explored this. If Alice measures her part of an entangled black hole pair, breaking the entanglement with Charlie's black hole, the wormhole connection should change. From an outside view, it becomes a non-monogamous state, and the corresponding geometry is thought to become non-traversable, maybe developing a kind of blockage inside.
So the physics stays consistent even when you measure things.
Exactly. And there's another interesting parallel. Entanglement itself isn't something you can just see directly in quantum mechanics, and these non-traversable wormholes aren't something you can just fly through or detect easily in relativity. The limitations seem to align.
Okay, stepping back then. If ER EPR holds, the implications are way bigger than just black holes, aren't they? It sounds like it's saying space-time itself isn't fundamental.
That's the most revolutionary takeaway. It flips the script on how we think about unifying gravity and quantum mechanics, instead of trying to force gravity into a quantum framework, quantizing gravity.
Which is incredibly hard.
Right. This suggests maybe we should start with quantum mechanics, with entanglement, and see how geometry, distance, even gravity emerge from that deeper quantum layer.
Like temperature emerging from atoms.
Exactly like that. Temperature isn't fundamental to one atom, it's a collective emergent property. ER EPR suggests spacetime is similar. Entanglement is the quantum thread sewing space together. If you cut the entanglement, maybe space itself falls apart or atomizes at some level.
So distance isn't fundamental either.
In this view, geometric distance might be related to the lack of entanglement, or maybe inversely related to the amount of mutual information. Things that are highly entangled are close in the quantum information sense, even if they appear far apart in the emergent spacetime we perceive.
And gravity.
Gravity might not be a fundamental force either, but more like an entropic force, a consequence of the universe trying to maximize entanglement, perhaps. It's the macroscopic effect of all this underlying quantum information rearranging itself.
Wow. So it's not about fitting quantum mechanics into relativity, but finding relativity hiding inside quantum mechanics.
That's the paradigm shift it proposes. It reframes the whole quest for quantum gravity.
And it completely changes how we view Einstein's spooky action, doesn't it?
It really does. That correlation isn't unmediated. There's potentially a physical ER bridge connecting entangled particles.
But crucially, it's non-traversable for ordinary stuff, right? So no faster than light messages.
Correct. These generic ER bridges are non-traversable, which preserves causality. No sending signals faster than light through entanglement. So the very feature Einstein disliked most about quantum mechanics might be the fundamental building block of the geometric reality he described so well with general relativity. The irony is incredible.
Absolutely mind-bending. But, okay, let's bring it back down to earth a bit. It's a beautiful idea, but you said it's speculative. What are the main hurdles or challenges EPR faces?
Oh, there are definitely significant challenges. A big one is generality. The connection is mathematically precise for these very specific setups, like eternal black holes in anti-de Sitter space.
Which isn't our universe.
Right. Our universe is expanding, it's messy, it's not ad-as. Extending the ER EPR dictionary to say any pair of entangled electrons in our universe. Well, we don't have a precise mathematical way to do that yet. It becomes more metaphorical, as critics like Peter Woit have pointed out.
So the dictionary is incomplete. What else?
There's a potential energy-mass discrepancy. If you just naively calculate the mass or energy needed to support an ER bridge connecting, say, an entangled electron and positron, you get a huge number, way bigger than the mass of the particles themselves.
That doesn't sound right.
It suggests either the calculation is too naive, or these wormholes connecting simple particles are incredibly subtle, maybe existing more in the quantum foam rather than as large geometric structures. Or maybe our understanding is just incomplete.
And what about actually testing it? Can we look for evidence?
That's tough. There are experimental constraints. For example, if an entangled photon were dragging a tiny wormhole around with it, that wormhole would effectively have some energy, which means mass. A massive photon would travel slower than light.
But we know photons travel at the speed of light very precisely.
Exactly. High-precision tests haven't shown any slowdown. So that puts tight constraints on any simple model where wormholes just stick to particles. And remember, the monogamy issue. Classical ER bridges only seem to match monogamous entanglement. What's the geometric dual of non-monogamous states? Still an open question. How do you think we could even begin to test something like this? It feels almost beyond experiment right now.
Yeah, those are serious obstacles. But it sounds like, despite these challenges, the idea itself has really sparked new directions in research.
Absolutely. It's been hugely influential, even if it's not fully proven. One really cool area is using quantum computers.
Simulating wormholes?
Kind of.
Yeah.
In 2022, Google's Sycamore processor simulated a simplified model of quantum gravity, the SYK model, that behaves like a holographic wormhole. They actually watched information scramble on one side and reappear on the other, matching the dynamics of information traversing a wormhole.
Wow, like a hardware test for quantum gravity ideas.
Exactly.
Yeah.
It doesn't prove ER EPR in our universe, but it shows these ideas are mathematically coherent and can be explored computationally. Theoretically, people are working hard to build a better dictionary, to connect more types of entanglement to geometry, and maybe move beyond ADS space.
Any chance of seeing hints in astronomy?
That's highly speculative right now. Maybe, just maybe, there could be incredibly subtle effects on gravitational waves from merging black holes or tiny signatures in the cosmic microwave background. But that's really pushing the boundaries.
So we've journeyed from 1935, Einstein's two big separate ideas, through the black hole paradoxes that force them together, arriving at this ER EPR conjecture, this potential unification of spooky entanglement and geometric wormholes.
Yeah, it's an idea that really tries to weave together almost a century of physics, suggesting that these bizarre quantum links might literally be the threads space-time is made from.
A huge paradigm shift. Space-time isn't fundamental, it emerges from entanglement. Gravity isn't fundamental, it's a consequence of quantum information.
And the beautiful irony. Einstein's least favorite part of quantum mechanics, the spooky action, might be the very foundation of his greatest achievement, the geometric theory of gravity. It truly redefines connection.
So here's a final thought for you to ponder. If distance, the space between things, is really just a measure of the lack of entanglement, what does that truly imply about how connected everything in the universe actually is? Connected in a deep quantum way we're only just starting to grasp.